Before we turn to the real data analysis, in section 6 I will describe some technical aspects of modeling with binary outcomes. I'll describe the statistical specification of the model. I'll talk about the identification of the model, which is a tricky subject in this case. I'll describe different estimators that you can use, and I'll describe some simulations to show under which conditions we can get good estimates. So on slide 51, I show once again the RI-ARI Probit model using the HAT specification, the residual specification. So we have the continuous random intercept variable here influencing y star at all time points, with loadings fixed at 1. And the dynamic relationship is among the residuals of those y star variables to have the separation of within person and between person variation. There are no direct effects between the y star variables, no direct effects between the y variables, but the direct effects are all among the y hat variables, the residuals. So we're working with continuous latent response variables y star, which when they exceed a threshold tau sub t, the threshold at time point t, you get y equals 1, and otherwise y equals 0. For each time point, the y star variable is decomposed into two parts. One part that does not change over time. I'll use the letter alpha here for intercept. It's the same thing as the I in the random intercept circle here. And the residual part, y hat, or y hat star as we write here. And the y hats are then regressed onto each other at the previous time point. So for instance, y2 hat is regressed on y1 hat with the regression coefficient beta, which is the autoregressive coefficient, the slope. So the beta sits here. And then we have a residual z, which is z2 in this case. So the residual y2 has its own residual, except for time point 1 where there is no previous influence. So y hat 1 is equal to z1. The variables here then are the random intercept and the t different residuals. And we're going to assume that all of them are normally distributed, which creates normally distributed y star variables. However, not all t residual variances can be identified. As we noted before, you get an indeterminacy in the model, so it's not identified. And a maximum of t minus 1 can be identified in principle, but in empirical applications, there may be far fewer variances that can actually be identified empirically. And the number of identifiable variances will depend on the data, will depend on the correlations across time, as well as the number of time points that you have. We're going to use the default of all residual variances fixed at 1, which I feel is often reasonable. So we're saying that this variance z2 is 1 across time, and it's also the same as the residual at the first time point. So there is an issue that is a little bit different than this residual, because this is a whole variable like y star, like y2 hat, whereas z2 is the residual. But since beta is less than 1 and often quite low, like 0.3, the variance contributed by y1 to y2 is fairly small. It's 0.03 times 0.03, so 0.09 times 1, which means that the residual here is going to be the major part, the variance of this is going to be the major part of the variance of y2. So that's an argument that even you can have equality of variances even between the first time point and the residuals of the others. On slide 52, we see these familiar correlation plots for the RI-ARI model. Again, showing the correlation between the first time point and later time points under different conditions of the AR value and of the RI variance, or the R square that is the amount of variance explained by the random intercept in the y star variables. These plots give a feeling for the identification of the model, as we will see as we move forward. Important part of understanding that is the correlation formula at the bottom, correlation between the first and later time points, consisting of the sum of two different parts, where the first part is psi, that is the random intercept variance in a metric that corresponds to the R² value. The second part is beta times 1 minus psi, where beta is to the power of t minus 1. So for instance, if you consider time point t equals 2, that's beta to the power of 1, where beta is the AR coefficient. You see then that when t increases, say t equals 10, you have beta to the power of 9, and since beta is less than 1, that term will go towards 0. So the second term disappears, and all you're left with is psi itself. And that's important from an identification perspective. You can take a look at the top right panel, and we see then that the line of psi is at 0.25, the R square is 0.25 here. So that's the bottom value, the asymptote, towards which all of the correlations head. Except for the highest AR, it's the other ones go down to that line fairly quickly, around time points 5, 6, 7. You go down even more quickly here, perhaps for RI variance 0.50. And the speed with which the autocorrelation goes down towards 0 has an impact on the empirical identification of the model. For a given number of time points in your study, identification may be easier if the AR is not large, not 0.75, as opposed to say 0.5, because then the correlations go down to the R² line quicker. And of course, having larger number of time points also helps in the identification. Now, the identification is essentially based on correlations across time, like we've looked at. We're going to allow the time-varying means, that is the probabilities of y equals 1, or in other words, as captured by the thresholds, are free across time, so no trend at this point. So the thresholds are identified by the proportions of y equals 1, while the rest of the model parameters, the RI variance, the autoregressive slopes, the residual variances, are identified via the correlations. There's no other information in this multivariate Probit model. So here's an example. I have simulated data according to this. T equals 10 time points, random intercept variance 1, which gives R square of y star approximately 0.5, autoregressive coefficient 0.3, and residual variance is 1. So I'm looking at the correlation between the first and another time point here. So then you have an initial correlation between time 1 and time 2 of 0.666767, which agrees with one of the plots. If you interpolate between AR 0.25 and AR 0.5. So you see here the correlation curve going down towards the lower asymptote of 0.5, the R squared for y star, fairly quickly. And the point here is that the RI, AR, and residual variances are chosen to fit the curve of the sample correlations at these different time distances. On slide 54, we take a closer look at the identification based on correlations across time. And we're going to focus on the large T case, that is having many time points. So the figure again shows correlations across time for an AR1 model and an autocorrelation of 0.3. And we see that the autocorrelation, the correlation across time goes down towards the lower asymptote of 0.5, already at t approximately equals 5 here. So thereafter, the correlation is contributed to by only the random intercept. That means that if we have observed correlations between time point 1 and higher time points further away, we then have sample information about the random intercept variance, the 0.5 value in this case, because correlations of longer time distances are solely due to the random intercept variance. So it implies that the random intercept variance is in principle identifiable. Now, what about the other parameters? Well, we know that not all residual variances can be free, so let's fix one of them. Let's take, for instance, the first one. So theta is the variance of Z1. Fix that to 1. And we already know what the random intercept variance is. And then let's focus on the correlations of time 1 and later time point. A correlation between Y1 and YT. And that can be expressed in terms of the standard correlation formula of covariance divided by standard deviations. The covariance for longer time distances is solely captured by psi. And at the first time point, then the variance of y star is psi plus 1. And at the later time point, it's psi plus theta sub t. So knowing a correlation, which is an observable quantity, and knowing psi, which we knew from previous reasoning, the only unknown is theta, t. So with t minus 1 such correlations, we can identify t minus 1 theta, t's. Now, what about the other parameters? Well, the other parameters are the t minus 1 autoregressive coefficients. Well, they can be identified from among the remaining correlations. Because with t equals 5, for instance, you have 10 correlations. You use 1 to identify psi, you don't need more than 1. 4 to identify the 4 thetas, and then 4 to identify the ARs. So that makes for 1 degree of freedom, only 9 parameters and 10 correlations, so 1 degree of freedom. Slide 55 then gives some examples of identification and counting the number of parameters. So with t time points, there are t sample proportions, and t times t minus 1 divided by 2 sample correlations. So if you take now the example of this binary outcome for the RI-ARI model and fixing the residual variances, we fix them to 1. You have t parameters for the thresholds, the unrestricted means, 1 parameter for the random intercept, and t minus 1 parameters for AR1. So we're focusing on the case of fixed, all residual variances fixed, which is more than we need, but it's going to be our standard approach. For t equals 3, there are then 3 thresholds, 1 random intercept variance, and 2 autocorrelation coefficients, namely 6 parameters, which is equal to the number of proportions and correlations, so you get a just identified model. With t equals 4, there are 4 thresholds, still 1 random intercept variance, and now 3 autoregressive coefficients. 8 parameters and 10 proportions and correlations, so 2 degrees of freedom. With t equals 8, likewise, we get 16 parameters for 36 observable proportions and correlations, so 20 degrees of freedom. Now, it's true that the first variance, as we discussed, has different meaning than the other ones because of no regression on previous time points. So you could be tempted to try to identify or estimate the first variance. And you can do that. The first variance is identified. In the best case, even t minus 1 variances are identified. But at least the first variance is often identifiable empirically. But typically it's not significantly different from the other variances, which are fixed at 1. So it's not significantly different from 1 that we fixed it at in the default setting. So depending on the parameter values and the data, some residual variances can be identified, but typically don't change the fit of the model, but it increases the standard errors of parameters. So it may not be worth the trouble. On slide 56, we turn to the estimation of the model. And we have three choices here: maximum likelihood, WSMV, and Bayes. Using maximum likelihood is not practical in this situation. We have this difficult combination of categorical outcomes and many continuous latent variables, where the number of latent variables leads to dimensions of numerical integration, and when there are too many such dimensions, the computations become impractical. So we're not going to use ML in this context. But ML in principle has the advantage of handling missing data optimally. It is in line with what we call FIML, that is, missing data under the so-called MAR assumption. An alternative is WSMV, which is a very good estimator. However, it does not handle missing data optimally, only handles missing completely at random, but not the more general MAR. It is, however, a very good estimator when the coverage is high, when you don't have that much missing data, because it's very fast and gives you also modification indices, and in this case, with high coverage, it gives estimates similar to the alternative estimators. A real breakthrough, though, in Mplus now is the Bayes estimator for this situation. It has the same advantage as ML in handling missing data optimally, that is, under the MAR assumption. Bayes, however, works quite poorly with a factor approach to the model, that is, the top way of specifying the model, where we explicitly create within factors using by statements. Instead, we use this y-hat approach in the algorithms for Bayes. So the y-hats are not unknowns like factors. When you have factors in Bayesian analysis, they are treated as missing data, which have the values of which have to be estimated in each iteration, in each Markov chain Monte Carlo step. But that's not true for the y-hats. They are obtained by subtracting from y star the random intercept. So they're obtained as a remainder. And this is described in this Sparrow-Mutén paper of 2022 RSEM, which will appear in the SEM journal. So that we're going to focus on the Bayes estimator in this talk. However, there's some models for which we have not yet developed Bayes, and then we will lean on the WSMV estimator. So on slide 57 then, I turn to simulations, where I should mention that some of the simulation runs are, output from some of the simulation runs are posted on the website of the Webtalk. So throughout the simulations, we have binary outcomes, time-varying thresholds, and time-varying autoregressive coefficients beta. No missing data, so therefore WSMV is not handicapped by not handling MAR missingness. Bayes results are quite similar to WSMV, but Bayes has somewhat smaller standard errors, typically, so which is advantageous. Parameter values are the ones I mentioned earlier, autocorrelations all 0.3, but not imposing invariant autocorrelations. Random intercept variance 1, residual variance is 1, R squared due to the random intercept 0.5, R squared for the residuals, there you have that low R squared 0.09, and then we have, and this is very important, low prevalence. So the proportion y equals 1 is only 0.2, and that is then corresponding to the real data in data set number 2 with the suicidal ideation and substance abuse. Now we're going to work with fixed variances here then first, and t equals 3 then It's a just identified model, as we mentioned before. It gets good results for 500 observations. And when I say that gets good results for 500, it means it doesn't give really good results if you go down below that. T equals 4 gets good results for n equals 500 as well, and so does t equals 8. So no improvement here with more time points in terms of the quality of the estimates and the standard error, because we don't hold any parameters equal across time. But you note here then, to do binary RI-AR1 modeling, you do want to have sample sizes of at least 500. Now, if you free the first variance, as we mentioned, the model would not be identified for 3 time points. T equals 4 gets good results for 2000. So you need a much larger sample to get good results when you start freeing the variance, because the standard errors get larger. T equals 8 gets good results for n equals 500. So here you benefit from having more time points as opposed to in the fixed variance case, because you have more correlations that identify the first variance and identify the random intercept variance. The free t-1 variances case, which I remind you again is often not a stable model in practice, and typically perhaps shows up with identification or non-convergence problems. T equals 4 is not identified. T equals 5 gets good results for n equals 5,000. T equals 8 gets good results for n equals 500. So there you have the rough outline of this situation for binary outcomes in the RI-AR1 setting